In this video, we'll introduce our work, WLST, Weak Labels Guided Cell Training for Weakly Supervised Domain Adaptation on 3D Object Detection. Let's look at the domain shape problem. These are some examples I visualized using the Open3D package. We pre-trained the 3D object detector PVR-CNN on the Waymo open dataset and test it directly on the TT dataset. However, due to the inherent domain gap between these two datasets, such as difference in point count distributions, we can observe that the model's performance is suboptimal. We have encountered quite a few false positives, missing detections, and inaccuracy in object size. So the performance gap between the detector trained on Waymo and the detector directly trained on TT is significant. To tackle these problems, one popular solution is using a cell training framework. So the workflow involves initially pre-training a 3D detector on the source domain. Then we generate 3D labels and select the ones with higher confidence to fine-tune the original detector on the target domain. Since these labels are not ground truths, we refer to them as pseudo-labels. However, the quality improvement of pseudo-labels is limited because those pseudo-labels are generated by the model based on its understanding from the source domain. Without using information from the target domain, we cannot effectively select high-quality pseudo-labels. As shown in the figure below, we can still observe many missing detections and false positives generated by the SOTA self-training methods. The figure shows that the SOTA self-training method falls in performance compared to the Oracle. Hence, a weakly supervised method aims to enhance the domain adaptation performance in a cost-effective way. Our idea is to leverage cheaper weak labels from the target domain, such as 2D labels. Motivated by the perspective geometry of 2D labels, we can adaptively narrow down the 3D search space for this vehicle, which is referred to as a frustum. Subsequently, we input this frustum into a model called AutoLabeler to generate a pseudo-label. Here are some examples demonstrating how the frustum helps to generate pseudo-labels. When facing missing detections, we can infer that an object should exist in this space. In the case of true positives, we can have greater confidence that pseudo-labels exist. For false positives, they can be easily eliminated since there is no corresponding frustum. Therefore, our approach integrates the AutoLabeler into the self-training framework to generate more consistent and robust pseudo-labels. We call this pseudo-label generation process a consistency fusion strategy. Our consistency fusion strategy is generally based on the geometry consistency and cost modality consistency of these pseudo-labels. First, we project the pseudo-label back onto the image and compute the 2D IOU with its corresponding 2D label, because a true positive tends to have a higher IOU than a false positive. Secondly, if both modalities agree on the need for a pseudo-label at the same location, there is a high probability that it is a true positive, and vice versa. Finally, we'll use these final refined pseudo-labels generated by our consistency fusion strategy to fine-tune our models. Here we analyze the pseudo-labels generated by these two modalities and explain how our consistency fusion strategy enhances the qualities of pseudo-labels. First, compared to AutoLabeler, the 3D detector has a larger field of view and operates at a scene level. Therefore, its strength lies in its ability to discern correlations between objects, resulting in higher recall. On the other hand, although the AutoLabeler operates at the object level, it effectively narrows down the search scope of pseudo-labels in 3D space, resulting in higher precision. Despite the strengths and weaknesses inherent in the pseudo-labels generated by these two modalities, our consensus fusion strategy adaptively improves precision while maintaining high recall simultaneously. Now let's take a look at some qualitative results. In the case of Waymo toolkit, our methods demonstrate the ability to generate higher quality pseudo-labels, exhibiting fewer missing detections and false positives, especially for vehicles located at longer distance. The figure shows that our method stands out as SOTA, particularly in terms of 3D average precision. In the case of Waymo to nuisance, our method exhibits superior performance as well. The results still show that our methods outperforms the previous SOTA models. However, adapting from Waymo to nuisance presents a challenging case, so there isn't much improvement in scores. There is an area where our work can progress further. So our main contributions can be summarized in three aspects. Firstly, we formulate and investigate WDA problem in 3D object detection, and underexplored yet practical tasks with the potential to enhance DA performance cost-effectively. Secondly, we propose a cost-effective self-training framework, WLST, which boosts DA performance in 3D object detection. Thirdly, our WLST framework underwent extensive evaluation on 3 widely used 3D object detection datasets, outperforming previous SOTA methods across all evaluation tasks. Thank you. Please refer to our code and paper for more information.